In this section, we're going to talk about initial value problems. So initial value problems are really problems that we've seen before, starting with Calculus 1. We had a function we wanted to integrate. Let's say we had something like y prime is equal to 2x plus 3. And we were given a point, maybe it was y of 0 is equal to 1, and we were asked to solve that. And we did that by saying we could integrate both sides. So what was really going on behind the scenes there before we did that, what made that step legal, is the fact that we could write y prime as dy over dx, and then we could separate those variables. Understanding that all of that would be multiplied by dx. And then we could integrate. So we would get y is equal to 2x squared over 2, which is x squared plus 3x, plus some constant c. So we said before this was called a general solution. We are going to call that the general solution to the differential equation, since that's technically what it is, with this guy being in the differential equation to begin with. But as long as you have some kind of condition, you could solve for c. And what that condition is really just a point that's on the graph of this function. So remember, this guy is a family of curves. In this case, it's a family of quadratics. And if I substitute this point into that family of quadratics, I can figure out what my specific c value is. So if we were to do that here, we would have 1 is equal to 0 squared plus 3 times 0 plus c, which means 1 is equal to c. So our specific equation, which we would call the particular solution for this initial value problem, is y equals x squared plus 3x plus 1. So we're really going to focus on some of those definitions really tied around this idea of an initial value problem, and then we're going to introduce the idea of a boundary value problem. So that's kind of the background as to what we're going to talk about. So when we talk about what we're looking at here, we're going to talk about the difference between these two, and then we'll go back up to that general definition. So in that first box, this is a first degree problem because we have that first derivative there. So this is a first order differential equation, if you will. Notice that if we want to solve a first order differential equation, I'm going to go down to our picture here, we could have different solutions. So this is your family of curves. But if we have an initial condition, then that means we have a specific point that's on that curve. And if I have this specific point that's on that curve, then I can find that specific equation that goes through that point that will satisfy that differential equation. If we have a second order differential equation, then we have, when we integrate, we're going to have two unknowns, a C1 and a C2, which means we're going to have two different initial conditions in order to find that particular solution. So in this case, if we were to integrate this, and notice that this function, they've got the second derivative by itself here. It's going to be in terms possibly of x, y, and the first derivative, y prime. So when we integrate, we're going to get this family of curves again. But if we want a particular one, we're going to have two conditions to find that particular one. Notice one of those conditions here is a specific point that is on the function y equals, and whatever this is, f of x in terms of x. Now, one thing I want you to notice with the second box, when we have those initial conditions, they are at one specific point. So I'm always using that same x value here, and that's going to be true for an initial condition problem or an initial value problem. So now let's go back up to this general idea. We want to solve an nth order differential equation. Notice that the way they've written this, they've got that nth derivative by itself. So whatever's over here could be written in terms of x's and y's and y primes all the way up to the nth minus 1 derivative. The higher the order here, the more conditions you're going to need to find a particular solution. So when we had a first order differential equation, we needed one initial condition. When we had a second order, we needed two. If we have an nth order, then we're going to need n initial conditions to satisfy that. And that's just going to allow us to find all of those constants. So let's look at a few examples. So in problem 41 in the exercises 1.1, we were asked to deduce that y is equal to c of x is a one-parameter family of the solutions of y prime is equal to y. So if we were to solve that, y prime is equal to y, we could solve that by separating those variables. So let me show you where this is coming from. So we have dy over dx is equal to y. The whole goal with separation of variables is to get all the y terms on one side and all the x terms on the other side. So we can do that by multiplying both sides by dx and then dividing both sides by y. And now we can integrate. And when we integrate dy over y, we get the ln of y plus some constant of integration, and that's going to be equal to x. Actually, instead of putting the constant on the left, I'm going to put the constant on the right. So it doesn't matter which side you put it on. You can put it on either side. Why we don't put it on both sides, let me go back and explain that. So we could do that. But ideally, you want to try to solve for y if you can. So if we moved this constant over, then we would have a constant minus another constant, which itself is just a constant. So instead of going through all of that to get to that final idea that there's a constant on one side, we can just write plus c on one side. So if we were to solve this for y, we can use the properties of logarithms. We know the base of the logarithm ln is e. The exponent is going to be x plus c, and that's going to be equal to y. Now, we can simplify this a little bit more. That's equivalent to e to the x times e to the c. Okay. Reason is, if we were to multiply these together, we would add the exponents because they have the same base. So these are algebraically equivalent. And now we have e to the c. Well, e is just a number, so about 2.71. And if we raise a number to a constant power, then we have another constant. So I'm just going to call that c1. E to the x is equal to y. So that's where they're getting this solution from. It's just using that separation of variables idea. Now in section 1.1, they would have given it to you and they would have said verify. We just went ahead and solved it. That was a simple one that we could solve. It's one you probably actually saw back in Calc 1. So if we talk about where these solutions are going to be defined, what interval would this work? The original differential equation would be defined from negative infinity to infinity. That solution, c1 e to the x, is going to be defined from negative infinity to infinity also. Now, what if we were to impose a condition, say y of 0 is equal to 3? That's going to allow us to figure out what that constant of integration would be for that specific problem. So we're going to have c1 e to the 0 is equal to 3. Then that means c1 is going to be equal to 3. So our particular solution would be y equals 3 e to the x. Whereas this guy was a general solution to the differential equation. So graphically, if we were to graph that general solution, we're going to see lots of different curves that go through there. And we could graph that using Desmos if we wanted to and create a slider for the C's so you could see that family of curves. What we were looking for here was a particular solution that goes through that point 0, 3. So here's that point 0, 3. This is the particular solution that satisfies that differential equation, and it goes through that specific point. So it's not just only satisfying the differential equation, but it's going through a specific place on the Cartesian plane. So if we were to change the idea of where this graph has to go, let's say it has to go through the point 1, negative 2, then that's going to end up changing our C value. So that means that y of 1 would be equal to negative 2. So that particular solution, we would have c1 e to the first is equal to negative 2. So c1 would be equal to negative 2 over e to the first, or e. And we could write that as negative 2 e to the negative 1. So there's our constant. So then our equation would be y equals negative 2 e to the negative 1 times e to the x. And notice we have the same base here and we're multiplying, so we could simplify that just a little bit further by combining those exponents. So it would be negative 1 plus x, or we could write x minus 1. All that's in the exponent. So notice this particular solution is much different than that particular solution. And all that has to do with that initial value. So if we were to graph this guy on the Cartesian plane, we want to go through the point 1, negative 2, which is here. And if we were to graph it, we would get this particular solution. So particular solutions will change and vary depending on what initial condition is given. Since this was a first order differential equation, we only needed one initial condition in order to figure out what our C value would be. So now let's talk a little bit about the interval of a differential equation versus the interval of the solution of a differential equation. So upcoming in section 2.2, we're going to be asked to show that if we have this differential equation, this guy is a solution. We could go through and verify that. If we wanted to, we could take the first derivative, substitute it in, make sure we get an identity statement. In this case, we would end up getting 0 is equal to 0. I'm not going to go through all of that. I'm just going to assume what they've told us is true and that this is definitely a solution to that differential equation. Now, if we impose an initial condition here, that y of 0 is equal to negative 1, let's substitute that in. So our general solution is this guy. If I plug in the negative 1, I have 1 over 0 squared plus c. And we're going to get c is equal to -1. So our particular solution is the equation y equals 1 over x squared minus 1. So notice this family of curves is going to look much different than the family of curves we talked about before for the last equation. We had exponential in the last example. Now we have a rational function for this example. So if we were to think about this guy as a function and think about what the domain would be for that particular solution, the domain for the particular solution would be everything except 1 and -1. And that comes from setting that denominator equal to 0. So we know x can't be 1 or -1. I'm going to write this in interval notation. So if we were to think about what this graph looks like, that graph would look like this. We would have two vertical asymptotes, one at -1 and one at 1, and we would have 3 different pieces for that solution. Okay, that's just thinking about this in terms of like a pre-calculus class. What would that domain look like as a function? And so now let's consider this as the solution of the differential equation. So if we were to talk about this as a solution of the differential equation, then the interval of the definition can be taken as any of those 3 pieces. So remember, differential equations, when we talk about the solution, it has to be defined on a continuous interval. Well, we are not continuous from -infinity to infinity. We have vertical asymptotes in here. So when we talk about the interval for this solution, it would be this piece, and then it would be this piece, and then it would be this piece. But now, if we now talk about that initial value problem, because we had an initial point, we actually got a very specific piece of this graph, and that initial point that we had was the point 0, -1. And the point 0, -1 lives here. So the piece that we found was actually this middle piece because of the way that particular solution, the point that was used for that particular solution. So then if we're talking about the solution of the initial value problem, there's the difference versus the solution of the differential equation versus the domain of the function. If we talk about the solution of the initial value problem, then the largest interval on which this function, this solution would be defined, would have to contain that initial point. Because the domain for the function is split into 3 pieces, and this point only lives in one of those 3 pieces, then we have to use the domain for that restricted piece. So this point lives here. This piece is bounded by this vertical asymptote and this vertical asymptote. So then our domain, our solution, our interval for the solution of the initial value problem would be this little piece here, which would go from -1 to 1. So it's all about that wording and what's going on with the wording. Are we looking for a domain of a function, or are we looking for the interval for the differential equation? Or are we looking for the interval for the solution of the initial value problem? So subtle differences in wording can change what's being asked in that problem. So let's look at another example. In this one, we have the same differential equation and the same solution, y equals 1 over x squared plus c. But notice that they are giving us an initial value problem, and that initial condition is different. So if we were to substitute in that initial condition, and this is an equals here, make that a little bit clearer. So we're going to have 1/3 is equal to 1 over 4 plus c. That means 4 plus c is equal to 3. So c is, again, -1. So this particular solution will be 1 over x squared minus 1, which is going to look the same as this guy, right? So if we were talking about the domain for the function would be everything except 1 and -1. If we were talking about the solution for the initial value problem, now I'm going to abbreviate that IVP. What interval, or what's the largest interval for where the solution is valid? So here's our -1 and 1. Here's our pieces. You have to think about, where does this point live? Well, this point lives at 2 1/3, which would be on this piece of the graph. So the solution for the initial value problem will have the interval from 1 to infinity. You have to think about where that initial value will live. So now let's look at a second order initial value problem. So we have the differential equation x double prime plus 16x is equal to 0. And they're telling us the solution is x equals c1 cosine 4t plus c2 sine of 4t. Since this is a second order differential equation, to find a particular solution, you have to have two initial conditions. Notice we have two initial conditions here. One is for a point that lives on x prime. Another is for a point that lives on x. And notice they're using that same x value again. That's how you know you have an initial value problem. So to solve this, and we'll talk about how they got this guy from that differential equation later. There are techniques we can use. But for now, we're going to assume it's true. We could go through and verify it if we wanted to, which would be a great exercise to do if you wanted to pause the video and to do that. But we're going to figure out what C1 and C2 is going to be. So let's do some substitutions here. So if we were to substitute in this information in for x, we're going to have -2 is equal to C1 times the cosine of 4 times pi over 2, which is 2 pi, plus C2 times the sine of 4 times pi over 2, which is 2 pi. We know sine of 2 pi is 0, cosine of 2 pi is 1, so -2 is equal to C1. And now we need to find x prime, since this initial condition lives on the derivative of x. So if we were to find that derivative, and I'm going to move this over so I have more room. Derivative of the cosine is a negative sine. This is a chain rule. Derivative of the angle is 4. Derivative of the sine is cosine. Derivative of the angle is 4. Clean it up. So we have -4c1 sine of 4t plus 4c2 cosine of 4t. And now we can do a substitution. If we substitute that information in, we have 1 is equal to negative 4c1 times the sine of 4 times pi over 2, which is 2 pi, plus 4c2 cosine of 2 pi. Sine of 2 pi is 0, cosine of 2 pi is 1. So we have 1 is equal to 4c2, which means 1/4 is equal to c2. So then, our particular solution, x, is equal to c1, which is negative 2 cosine of 4t, plus c2, which is 1/4 times sine of 4t. So that's where that particular solution is coming from. In this case, we ended up coming up with really a system of equations, but this one was simple to solve.